All right, so what about something like this? When we've got a rational function and we want to get a quick sketch of it, right? What are the things we do? There's a couple different, there's kind of an order to the way we approach these. One thing we want to do, we want to get the horizontal asymptote. What's our rule for finding a horizontal asymptote? Right, that's when we take a limit as x approaches plus or minus infinity. We'll do this in more detail in a couple of years in calculus, but for now, what do we do? If what's going to be the horizontal asymptote here, and why? Remember our rules? So so the limit of f of x as x approaches plus or minus infinity, as we go infinitely far to the right or the left, what are we going to get? What's the rule? If we've got a rational function where we've got the same order in the top and the bottom, the polynomials are the same order, meaning that the highest power of x is the same top and bottom. What do we do to find the horizontal asymptote? Say it again. 7071, I think. If that's not it, I don't know. Remember what we do? What do we do? Say it again.
Divide the numerator by.
Well, okay, we don't even have to do that. We can't. But we don't even have to do that. We can just use the rules if we got three different cases. If the order of the top, so we get the same degree polynomial or order polynomial on the top as the bottom, then all we have to do is take the ratio of the leading coefficients, right? So in this case, we get -3/1. So that's telling us that the limit, if we go infinitely far right or left, the limit is -3. In other words, we have a horizontal asymptote at y equals -3. Okay, so that's one important thing. That tells us what the tails of the function are doing. So this wouldn't work, would it? This is a horizontal asymptote at +3, right? We'll look at the other cases. We'll look at two more examples. Look at the other cases also. So what about vertical asymptotes and holes? What do we have to do there? Or if this was your question, what are we going to do in a case like this? What are we going to try to do? Okay, we'll try to find zeros, presumably by factoring, right? But are there any zeros of this function on the bottom of this expression, x squared plus 25? There's not going to be zeros, are there? That's for a couple of reasons. It doesn't factor because it would be a sum of squares pattern, and there isn't a sum of squares pattern. That's the one that's missing, remember. And then the other thing is too, if we were to set that equal to 0, oops, x squared plus 25, equal to 0, you can see right away you're not going to get real results, are you? If we isolate x, we're going to subtract 25 from both sides, and you'd get x squared equals a negative number, which is going to give you i's, right? So there aren't going to be any zeros of the denominator. So let's kind of refresh our memories about what that means. Zeros of the denominator are places that we have to exclude from the domain, because that's the unbreakable rule in math. For real numbers, you can't divide by 0, right? So those are the places where the function would be interrupted. Those are values we have to exclude from the function. There's two things that can be happening at those places. What would the math gods do? So if an ant were walking along the function, it would prevent him from stepping on those x values. What are the two things that could happen? We could get asymptotes. The math gods could throw up an infinite wall that he couldn't pass. Okay, that's pretty dramatic. What's the other thing that could happen? Yeah, they could just take a point out, right? They could create a hole in the function where he couldn't stand because they'd remove that point in the function. Are there going to be any of those in this case? No, right? There are no exclusions. The domain would be all real numbers here, right? Okay. What about the top? We could simplify the top a little bit, couldn't we? If we were to factor out a -3 on the top, what are we left with? X squared minus x minus 2, is that right? okay, over x squared plus 25. So what does the top factor into? What do you think? Jessica, what's the top factor into? What are my magic numbers going to be? Multiply to -2, add to -1. -2 and +1, good. So my zeros would then be what? 2 or -1. Okay, so those are zeros of the top. There are no zeros of the bottom. So what does it mean if you have a number that is a 0 of the top but not the bottom? What does that correspond to on the graph? X-intercept, sure, that's a 0 or an x-intercept, right? Okay. What's it mean if you have a simultaneous 0 top and bottom? Whole, good. Exclusive 0 at the bottom? Vertical asymptote. So that's really what we need here, isn't it? We need to know that we've got x-intercepts at 2 and -1. We've got a horizontal asymptote at -3, and that's about it for this function. There's not a lot more we can do, is there? There's not much going on. So we would just have to go in search of that function. So where are we at? 2 and -1. That's it right there, isn't it? Everybody agree?
Yep.
Okay. That's the one that fits. -3, yeah, that's it. I think that's the right one. I can't tell when it's compressed like this, but I think that's the head. Okay, got it. All right, how about, let's try one of these. Oh, is it there? Oh, okay, good. That was fast. All right, so what's the horizontal asymptote going to be there? -2, everybody agree? Because I've got an x squared, the order of the top polynomial is 2, order of the bottom is 2. I look at the ratio of the leading coefficients. So let's pick one that's different. What about that one? What's going to happen there? What happens if the top is bigger order than the bottom? It's bigger by 1. Remember what we do here? If the top is second order, bottom is first order. Is there a horizontal asymptote? There's not going to be a horizontal asymptote, but there will be a slant asymptote. If the top degree of the top polynomial is 1 bigger than the bottom, if we divide this out, what do we get? This is a pretty easy one to divide out. If we divide this one out, I can just, we lucked out here. If this had been like an x minus 4 or something like that, we'd have to use probably synthetic division or long division if we chose. But if we're just dividing by x, how could I do this without even having to do any kind of fancy division? What do you think? Any ideas here? Okay, do you see any ideas how I could just like really quickly figure out what I'm going to get if I divide this thing by x? Well, I mean, we haven't talked about this. It's just something that I think is kind of a cool thing to, this is just a problem where it happens to work. If this were x minus 4, we'd have to put it, do the whole synthetic division thing to figure out what the quotient is with the remainder, right? But if we have something like this where I just have a single x in the bottom, couldn't I just split this into 2 separate fractions and simplify each one, right? So I could write this as negative 2x squared over x plus 18 over x. And what does that reduce to? Negative 2x, okay, and then I get plus 18 over x, right? So this is what the quotient is. If we're taking a limit here, if we're taking the limit of our function, and let's write it in this form, right? Let's write it in where we've simplified the quotient. The limit of negative 2x plus 18 over x as x approaches plus or minus infinity, what's going to happen in the limit that x gets really big? Well, what's going to happen to that fraction? It's going to go to 0, isn't it? Right, in the limit. Okay, and so we're left with just the negative 2x part, right? Well, what does y equal negative 2x look like? Well, I mean, but what's if I were to graph that function, what's that look like? That's a line, right? It's just, that's a slant asymptote. It's just a line with a y-intercept of 0 and a slope of negative 2, right? So if, and we didn't spend a lot of time on this kind, but if, I want you to get a little practice on these now. If you've got a situation like that where the numerator is 1 degree higher than the denominator in a rational function, then when you divide it out, whatever the part of the answer is that doesn't include the remainder, that is the equation of the slant asymptote, because the remainder is the part when you take the limit that's just going to disappear completely, right? So we know then one piece of information we have about this function is that we have a slant asymptote at y equals negative 2x, right? And those asymptotes are really important. They give us the bones of the graph, right? The skeleton of the graph. Okay, what about the rest of this? Let's look. What if I factor the top? Drew, what can I factor out in the top? Negative 2, good. Leaving me with x squared minus 9. What does x squared minus 9 factor into? X minus 3, x plus 3. Good, so I get divided by x. So let's summarize this then. What are going to be the zeros of the numerator? Matthew, what are the zeros of the numerator? If I set it equal to 0 and solve.
3.
And
Negative 3.
negative 3. Those are exclusive zeros of the numerator, right? They're not shared by the denominator, so what are those going to be? X-intercepts. All right, so we've got x-intercepts at x equals plus or minus 3. And what's the only 0 of the denominator? 0. And so that's an exclusive 0 of the denominator, so what's that going to be? Vertical asymptote. Okay, so then that gives us a lot of stuff. The only thing we're probably left lacking here is what's happening with that vertical asymptote, right? We know if we were to do a sketch of this, and like that could work, right? Hang on, no, that can't work. It's wrong. Okay, that could work right there, couldn't it? That could work, right? Everybody agree? We've got a vertical asymptote at x equals 0. We've got a slant asymptote that's y equals 2x, right? And we have x-intercepts at negative 3 and positive 3. Well, in fact, you know what? That's the only one that can work, isn't it?
Isn't it negative 2x?
Oh, it's negative 2x, you're right. So it's backwards. Yep. So, whoops, no, not that one. Bet it's that one. Right there. Does that make sense? Okay, and this is one, actually having that slant asymptote, you'll find, as you do more and more of these, you know, this year and in the future. That's pretty handy because a lot of times with the slant asymptote, there's really only one way that this thing could go. If this had been like a horizontal asymptote, or let's say it had been a horizontal asymptote at negative 2 and x-intercepts, well, I mean, there's a couple things that really could have happened, technically. You know, it could have gone up along the vertical asymptote, or it could have gone down along the asymptote, right? But in this case, that's really all that can happen if we're going to hit those points. Yes, sir.
Isn't there another way that slant asymptotes can be shown?
There is, yeah. What were you going to suggest?
Between the two asymptotes.
Oh, you mean up here?
Yeah.
But then how's it gonna go through those x-intercepts?
Yeah, but just in general.
Oh, in general, right, in general there would be, you're right. So if we didn't know that there were x-intercepts, and the thing about this, you're kind of entering the part of math where, I mean, every problem just starts to be so different. It used to be back in the day, you know, there were just a bunch of problems that all looked pretty similar, but now everything looks pretty different. I mean, you have to kind of just take some basic framework for a problem and apply it to each, you know, in each case it's going to be different. It's even way more so in calculus. In a situation like this, yeah, everybody see what Alg is saying? I mean, if we didn't have those points, there's two things that could be happening. It could be sticking to the asymptotes there, or it could be sticking to the asymptotes there and there, right? But because we know it goes through those points, it has to be this case, okay? All right, let's look at just one more quick one, if you want. Okay, what about one like this? What about something like that? Horizontal asymptote. If the degree of the bottom polynomial is larger than the degree of the top, what's the horizontal asymptote going to be? Y equals what? What's it going to be? 1. Not 1. Think about, we're taking a limit, aren't we? We're answering the limit as we go infinitely far to the right or the left. Where do we end up? Because that determines what the horizontal asymptote is going to be, right? What y value do we approach? So if we take this limit, what are we going to get? Now there's a couple ways we can approach this. There's a really good shortcut, a way to remind yourself. But I want you to think about this conceptually for a second. As x is approaching plus or minus infinity, how does the behavior of the bottom compare to the top? They're both going to be infinite, aren't they? But there's a really important distinction here.
Doesn't the bottom go like faster?
It does, right. The bottom is going to infinity, but it's going to infinity infinitely faster, right? And so it dwarfs the top, right? And so what's the answer going to be then? If the bottom is growing, if the bottom is growing infinitely faster than the top, what is the limit approach then? 0, sure. There is a way you can kind of do this that maybe, well, it's not better, it's just consistent with what we just said. What if we wrote it like this? If we wanted to include an x squared term, what would the coefficient need to be? 0, right? Okay, so we could write this. Did I show you this trick? Okay. 0x squared plus negative x plus 1. And then this would look like the form where the degrees are the same top and bottom, right? What was our rule for that? If the degrees are the same top and bottom, we just take the ratio of the leading coefficients, and 0 divided by 1 is 0. So that way works also, right? Either way you go, though, you end up with a horizontal asymptote at y equals 0, so just the x-axis, right? Okay, going a little further, what are the factors? Well, let's factor the denominator. What do we get if we factor the denominator? On the top, we just get negative, we factor out a negative 1, I get negative x, quantity x minus 1. What's the bottom factor into? What are the magic numbers?
X plus x minus 1.
Okay, so then I end up with zeros of the numerator, or just one of them, at 1, right? Zeros of the denominator are 1 and negative 6. Okay, so what's going on then? So where's there a hole?
1.
At 1. Okay, we get a hole at 1 because it's a shared 0. And we get, what's that? vertical asymptote. Okay, good. So we can find one like that. So we need horizontal asymptote. Okay, so that's looking pretty good there, isn't it? Right? That checks all the boxes so far. We got vertical asymptote at -6, horizontal asymptote at 0, hole at +1, right? The only thing that we don't know here is the behavior, is the asymptotic behavior correct? Because there's a couple other things that could be happening. What could be happening, as the function approaches the left side of our vertical asymptote, it could be going up or down, for instance, right? So how do we find out? What was our trick for that? How did we know what the behavior was? It's been a while, right, since we talked about this. Maybe we did something like this. We said we're going to take a limit of f of x, and there's f of x. It's in factored form right there, right? The limit of f of x as x approached what? What's going to be the value that's going to tell us the behavior, the asymptotic behavior on the left edge of this vertical asymptote? X is going to have to approach what? Say it again. -6, but we have to be very specific. It's going to approach -6 from which direction? From the negative side, okay. And so that's going to look like a decimal like what? -5.999 or -6.001? 6.001, right? Okay. So then if we evaluate the behavior, let's take this limit. In calculus, we'll call this, we're going to evaluate the limit directly, right? We're just going to plug in, see what all the factors become. So we're going to get a negative, and then -6 minus 1 would just be approach -7. Everybody agree? So on the top, we could just say 7, right? What about the bottom? We're going to get, from this factor, we're going to get a 7. And what about here? What's that going to look like? As we approach -6 from the left, is that going to be slightly negative or slightly positive? Slightly negative. Okay, so we're going to get 0 minus, and oops, that's a -7, isn't it? Right? Everybody agree? So then we end up with a non-zero number on the top divided by 0, which means infinity, right? But what's the sign going to be? It's going to be positive because I have an even number of negatives in my quotient, right? So that part checks out. If we do the same thing from the other side, as x approaches +6, on the top we'd get a -7. On the bottom we would get 0 plus times +7. Everybody agree? Did we do that right? Is that right? I'll hold it. No, I got that backwards. That's positive and that's negative, right? Those didn't change. Everybody agree? But what's the sign going to be then? Negative. So that's the right one then, isn't it? We get the right behavior, right? We're getting the right kind of asymptotic behavior on our vertical asymptote, so that's got to be it. Okay, make sense? This is pretty. We've never done this in Algebra 2 before. This is pretty cool that you guys are doing this stuff. I mean, this is not that it's like super complex, but this is way beyond. I mean, this is literally the stuff that we used to not touch until calculus. So it's kind of good that we're starting to talk about this stuff earlier. All right, have at it. I think that